All right, everyone, this is where we wrap up everything we've talked about this entire unit. So we're going to put together Newton's three laws. So the first law, again, an object in motion will stay in motion. If an object is moving, it is going to keep moving until something stops it. If an object is stopped, it is going to stay stopped until something starts moving it. Second law is that the net force is equal to mass times acceleration. This is specifically that net force. Back to the first law, that is the something that makes something move. And then this third law is when two objects interact, those two forces between those two objects are equal. We're gonna put this all together in these problems. I'm so pumped. I love this. All right, so there's two different methods for doing this. What method one is we're gonna solve it as two different systems. And I'm gonna do the same problem twice to show you we can do that. So method one, two different systems. We're gonna decide which direction is positive. We're going to draw a force diagram for each object. We're going to write F equal ma equations for the masses and solve for our unknowns. Method two is we're going to treat the two objects as one object. We're going to draw a force diagram for if the objects were one object, write an F equals ma equation, and solve for unknowns. There is a time and place for both methods. So I'm going to show you when the time and place is by doing it this way. So here's our situation. We're going to use method one, so that's the two object method. We've got a block pushing on another block, being pushed by a hand. So we've kind of got three things here. So we want to know what is the force between the two objects. So I'm going to start by drawing a force diagram. So I'm going to draw it for each object. I'm going to try to stay color coordinated here. So we've got force gravity, force normal. We've got an applied force. This is that 3 Newton force. But because A is touching B, there is a force on A from, I'm just going to call that FB, just so we know that's the force from B. And there's no friction. Thank goodness. There could be friction, but not yet. On our other one, we've got force gravity. It's a bigger force gravity, so I'm going to note it. Force normal. Now here, the hand is not touching B, so there is no force applied from the hand on B. But there is a force, I'm going to call this force from A. Big A, not applied. Difference. Now looking at this, I need to decide, I have to determine what force does A exert on B, and I have to determine my paired forces. I know it's the force that's causing these two to interact with each other. If A applies a force on B, B applies a force on A, that's my paired forces. When I do my equations, those two forces are equal to each other. So we want to solve for what's the force, that numerical value for those forces, and what's the acceleration of my system. So I'm going to follow my steps. I'm going to sum my forces, and I'm only going to care about the x direction here because in the y direction, we don't have acceleration. So I'm just going to do the x direction. So sum of forces on my orange block, block A, is equal to ma, which is equal to our applied force minus force B. On the other side, I'm going to do B's real quick. Sum of forces in the x direction acting on B is equal to ma, which is equal to Fa. There's no other force there. I'm going to plug in the numbers I know. I know that block B has a mass of 10, so 10A equals Fa. Fa equals Fb. I'm going to write that in the middle just so I don't forget that. Fb and Fa are equal because that's our Newton third law pair. That's why we've been waiting to do these problems. And I'm going to plug in my numbers for this one. So I got 5A equals, my applied force they told me was 3 minus FB. So looking at this, if FA equals FB, I've got an equation for FA right here. I've got an equation that say FA is equal to 10A. I'm going to take that and plug that in right here to this equation to solve for A. So I have 5A equals 3 minus 10A. And from here, it's just an algebra problem. I'm going to add 10A to both sides. So I have 15A equals 3. And then I'm just going to divide each side by 15, which gives me 3 divided by 15, which means my whole system has an acceleration of 0.2 meters per second squared. So that is the third one. I kind of work in random orders on these. It's okay. Once I have my acceleration, to solve for what force does it exert, I'm just going to take it and plug it into my other equation. So I'm going to look at this and I can see, I'm going to move my face real quick. I can see that 10 times 0.2 is equal to FA. And 10 times 0.2 is just 2. So FA is equal to 2 newtons, which means FB is equal to 2 newtons. That's an example of method 1, breaking it into 2 separate parts. I'm going to do the exact same problem again, but put it into one part, part 2. So part 2, how do we do this? We're going to treat them like they are one object. So this whole thing is just a 15 kilogram block. So I'm going to draw a force diagram for it. All right, we got force gravity, we've got force normal, and my 15 kilogram block is just being pushed by an applied force. So we're going to sum our forces. We're going to say it's equal to MA, which is equal to F applied. My mass is 15. My applied force is 3, which gives me the same acceleration of 0.2 meters per second squared. So I was able to do this one and this one. But with method 2, I'm not able to jump right into what force does A exert on B because I'm treating them as one object. If I'm treating them as one object, there is no force exerted between them because they're one object. This is an example of when I would be advantageous to use method 2 versus method 1. Method 1 is really, really useful for when I'm looking at that interaction force. Method 2 is super useful if I'm just looking for the acceleration of the entire system or the acceleration of the blocks. So it depends on what the question is asking for when it's useful to use each. You can see with method 1, I was able to calculate both of those, but with method 2, I was only able to calculate the acceleration, not the interaction force. Let's try one more example here. We've got a 7 kilogram block that's attached to a 3 kilogram box that's pulled by rope 1. The 7 kilogram box is pulled by rope 2 with a force of 25 newtons. So we actually are given a force down here. That's really useful for us to know. So this is 20. I'm going to add this to my picture up here. So it's 25 newtons. Determine the accelerations of the box and the tension in block 1. The coefficient between the friction and the ground is 0.012. So that's for both. I'm gonna kind of use a merge of 1 and 2 now just to kind of help us out. So I'm going to start by drawing my force diagram. I'm going to keep my coloring because I got a green box, so that's going to be my green box one. I'm drawing all the forces acting on my green box. I'm going to use, I don't want to use yellow, so I'm going to use purple. My other box is going to be purple. So we've got force gravity. It technically should be bigger if I were drawing it to scale, but I'm trying to save some space. Force normal. We've got a tension. I'm going to call this tension 2, and I'm actually going to go back and call the other one tension 1, just because I do have 2 tensions going on here because we have 2 ropes. And then for this, I've got the rope is touching this block, so we've got tension 1, but also we're going to have friction, so we're going to have force friction here. So that is one way. That's kind of my approach if I'm going to do this with a method 1 approach. I'm also going to use a method 2 approach because it's going to make it a little easier because I'm going to treat both blocks as one. We've got force normal, we've got force gravity, we've got a tension, this is tension 2, and we've got a friction. I'm going to do this because the question's asking me first to solve for the acceleration of the boxes and then find T1. So I might be able to avoid some messy work if I can just do that. So looking at this, I'm going to sum my forces in the x direction, and both blocks are as if I'm treating them as one block. So MA equals T2 minus force friction. I'm going to expand this equation a little bit. Instead of force friction, I'm going to say, oops, not minus. I'm using a new editing tool, so trying to learn how to use this new one. And force friction is mu Fn. But I'm going to take it one step further because Fn in this situation, since there's only two forces here, Fn is equal to force gravity, which is mg. So if I want to solve for the acceleration of my system, I'm going to move my face a little bit. I'm going to block some words, sorry. If I want to solve for the acceleration of my system, I'm going to add so the total mass is 10. Acceleration is what we're looking for. We're told the force of the rope 2 is 25, minus our coefficient of friction of 0.12, times our mass of 10, times g, which is 9.8. So using method 2 and treating them as one object, I can just solve for that acceleration right away. And the acceleration of the objects are going to be the same because they're being pulled at the same rate. So this gives me 10A is equal to, and I got to plug all that in my calculator, 25 minus 0.12 times 10 times 9.8, which gives me 13.24. Divide each side by 10. So this time I have an acceleration of 1.324 meters per second squared. That is the same acceleration for both sides. I'm going to move my face to cover this work now so I can do the other side. So my acceleration, done. Now we have to solve for what the tension in rope 1 is. Now, I can do this either way. I can use either one of these two objects. Now, I personally, when I'm trying to decide which object in my method 2 to choose to do my equations for first, I'm going to try the simplest one to see if I can use that one first. So force on the green box is equal to MA, which is equal to tension 1 minus force friction. And we're just solving for the tension 1. So if I don't have to use the one with tension 2 anymore, I'm not going to. So the mass of the green box is 3. My acceleration we just calculated is 1.324. Tension 1 minus, and we know that friction, I forgot, is mu mg. So I'm going to plug in 0.125, 12 times 3 times 9.8. So you can see here, I can definitely just use this one to solve for it. You could have used the purple one and you would have gotten the same answer. So on my right side, on my left side of the equation, I get 3.972 equals T1 minus 0.2 times 3 times 9.8, which gives me 3.528. If I add that to the other side to add my two numbers together, you can get a tension 1 of 7.5 newtons. I would really, really encourage you to try this with the purple one now. Go back, try to solve for that tension 1 using the purple side to see if you can get the same number. Because ideally, you should get the same number if you're doing this problem right. All right, that's all there is for this, for the entire Newton's Law forces unit. Really, it goes into, can we identify forces? Can we draw a force diagram? Can we set up our equations? And then can we use it to solve for an unknown? That process is going to remain the same throughout the entire course, really setting that up. And if you can learn any skill super well, it is this unit. Let me know if you have any questions. You guys are doing awesome.